Today we're going to be talking about SN1 versus SN2 reactions and mechanisms. Before we can get into what each mechanism looks like, we need to understand what the name of the mechanism means. For both SN1 and SN2, the S stands for substitution. So in this mechanism, we are substituting something for something else. N tells us that it is a nucleophilic substitution, so a nucleophile, which tends to be a base, will come in to substitute for our leaving group. The number, 1 or 2, tells us the number of things involved in the rate-determining step. If one thing is involved in the rate-determining step, that means the leaving group is going to be kicked off and a carbocation will form. If 2 things are involved in the rate-determining step, such as an SN2, that means that the nucleophile will come in and kick out the leaving group to avoid the formation of the carbocation. Anytime a carbocation formation or avoidance of a carbocation formation is involved in a step, that means that that is the rate-determining step. So we're going to look into actually doing this mechanism. Here I have pentan 3-ol, and on the third carbon I have an OH group, which is my leaving group. It's the only thing that I can actually kick out of my molecule. So before we can get started to determine if this is SN1 or SN2, we need to look at what kind of carbon is the leaving group on. Is it on primary, secondary, or tertiary? And in this case, because there are 2 carbons stemming off of that carbon that the leaving group is attached to, we say that that is a secondary carbon. So because we have a secondary carbon that the leaving group's on, it gets a little tricky because we need to pay attention to another thing. We have to pay attention to what kind of solution the mechanism's happening in. Right now I have it in heat, but I'm actually going to put it in CH3OH. And this is a protic solution, meaning it can support a charged molecule in solution because it can hydrogen bond. That OH group makes it possible to hydrogen bond due to the difference in electronegativity between the O and the H. So if it's a protic solution, that means it can support a charge. And if it can support a charge, a carbocation will form. The carbocation will form in an SN1 reaction because there's only one thing, one molecule in the rate-determining step. And that single molecule in the rate-determining step is this pentan 3-ol that we're working with. So it will help stabilize the carbocation and a carbocation will form. Okay, at this point in time, I drew in the electrons on the oxygen, and I'm showing that the electrons are going to grab the hydrogen. So the more electronegative of the 2 atoms involved is going to take the less electronegative. And as you see, when we take off that hydrogen from the bromic acid, because bromine is more electronegative than the hydrogen, it gets to keep those electrons. So we add a hydrogen to that OH, that hydroxyl group, and that causes the oxygen to have a positive charge because it has 1 less electron than it requires in its natural state. At this point, because it's an SN1 reaction, only this molecule will be involved in the formation of the carbocation. We can kick out that stable leaving group because the leaving group is just water. And then a secondary carbocation can form because the solution, the protic solution, can support that formation of the carbocation via hydrogen bonds. That water is just going to settle in solution, and at this point, now we have that bromide, because it has a negative charge. It's our anion. Since we have that in solution and a positive carbocation, the bromide is going to come in and it's going to fill the spot where the water left. So we'll show from the electrons to where it's going to go, and you have your final product with the bromine in the place of the hydroxyl group at the end. This is how an SN1 mechanism will go. Again, if you're at a secondary carbocation, or if you have a leaving group attached to a secondary carbon and the solution is protic, it will go SN1. I'm going to show you in a second
how we can switch this to an SN2 mechanism. If you ever have a tertiary leaving group, a leaving group on a tertiary carbon, it's going to go SN1 because that carbocation can always be supported. If you have a primary carbon, a leaving group on a carbon attached to one other carbon, it can never go SN1. You can never form a primary carbocation, and you will always go SN2. So I'm going to show you how we're going to switch this to an SN2 mechanism. When it comes to leaving groups on a primary carbon, we don't necessarily need to worry about the solution that it's in because it will always go SN2. Even if it's a protic solution, it still tends to go SN2. When the leaving group's on a tertiary carbon, it will always go SN1 despite the solution, whether it's protic or aprotic. So just keep that in mind. Secondary carbons, when a leaving group is on a secondary carbon, that is when we need to pay attention to the solution. Okay, now it's time to switch gears. We are going to be using all the same reactants. Our leaving group is still on a secondary carbon, but because our leaving group is on a secondary carbon, we need to pay attention to the solution. So what I'm going to change is the solution from a protic solution to an aprotic solution. And that aprotic solution, I'm writing here on the board, it's going to be DMSO. DMSO cannot support a carbocation. So we can't form a carbocation if it cannot be supported. There's other solutions that are aprotic. Typically, something that I use as a telltale sign to know if it's protic or aprotic is can it hydrogen bond. If it can hydrogen bond, it's protic. If it cannot hydrogen bond, it is aprotic and it cannot support the formation of a carbocation. So we have DMSO as our solution at this point in time, and that means that we're going to have to change up what happens in this mechanism. So I just crossed out all the steps that we did. We're still going to get the same product, we're just going to have to go about it a different way. The reason I crossed out that first step is we need more than one thing involved in the rate determining step. And in that first step, we are forming a carbocation with one thing. But this is an SN2 reaction, so we're going to need two things to avoid the formation of a carbocation as our rate determining step. So it's kind of going to be a 2-for-1 deal. And in this SN2 reaction, we will have a backside attack with the nucleophile because it's coming in at the same time we're kicking the leaving group out. So I'm going to be leaving that step where the oxygen steals the hydrogen from the hydrobromic acid and forms a water as a leaving group. Again, the oxygen is going to have a positive charge on it. It doesn't have 6 electrons assigned to it to keep its neutral charge, so it takes on that positive charge, and we still form that bromide in solution with the negative charge. Here's where the difference comes in. Again, there are two things involved in the rate determining step. Those two things are the bromide and our substrate. The bromide's going to do a backside attack, and as it does that, it's going to kick the water out. And because the oxygen is more electronegative than the carbon that it's leaving, it gets to keep those electrons with it, form water, and the bromide gets to attach where it previously was. So again, you can see we ended with the same product, we just went about it a different way. Two things were involved in that rate determining step. One, the bromide, and two, the substrate. And we ended with the same exact products, we just had to go about it a different way because we could not support the formation of a carbocation with the aprotic solution. If this were in a protic solution, we would go through those steps that we were going through in the previous reaction. If this leaving group was on a tertiary carbon, it would go through an SN1. If it was on a primary carbon, whether it was in a protic or aprotic solution, always SN2. You can never form a primary carbocation, so to avoid it, we need two things involved in that rate determining step to kind of skip over that carbocation formation. Again, the rate determining step is always when the carbocation is formed or when we are avoiding the formation of the carbocation, because forming it would be too unstable. I hope this was helpful in determining when to use an SN1 and an SN2 reaction. More videos to come about organic chemistry, and please leave a comment below if you have any questions that you'd like to be answered.